Okay, this is the lecture video for section 2.2 in My Open Math, formerly section 1.3 in MyLab Math. In this section, we're going to be taking a look at word problems, also known as models and applications. We're going to concentrate on a strategy for solving such problems, which incorporates 5 steps and is typically discussed in most math books as a process for dealing with application type problems. So the 5 steps are mentioned here. Step 1, read the problem carefully several times until you can state in your own words what is given and what the problem is looking for. Let x or any variable represent one of the unknown quantities in the problem. In step 2, if necessary, write expressions for any other unknown quantities in the problem in terms of x. Step 3, write an equation in x that models the verbal conditions of the problem. Step 4, solve the equation and answer the problem's question. Check the solution in the original wording of the problem. Okay, so what I'm going to do is demonstrate these 5 steps in this first example. Okay, so here is just a visual for you, a diagram that illustrates that over the span of 78 years, you spend a portion of that 78 years sleeping, a portion of it working, a portion of it watching TV, doing homework, eating, socializing, and shopping. And this is just a bar graph that shows how many years you spend doing each thing. These are the average number of years coming up the y-axis spent for each of these activities. So let's read the example that goes with this diagram. It says, use the 5-step process to solve the following problem. According to the American Bureau of Labor Statistics, you will devote 37 years to sleeping and watching TV. The number of years sleeping will exceed the number of years watching TV by 19. Over your lifetime, how many years will you spend on each of these activities? So we've read the scenario and we're going to try and break it down into the 5 steps that it was discussed in this strategy. Okay, so step 1, I've broken it down for you. We've already read. What is the smaller quantity? Well, in this particular scenario, they say that the number of years sleeping will exceed the number of years watching TV. So the number of years watching TV is the smaller quantity, and typically the smaller quantity is the one that we represent with just x, whereas the larger quantity is represented also using x, but in terms of how you have represented the smaller quantity. So what is the smaller quantity? Years spent sleeping or years spent watching TV. I just discussed that. Smaller quantity should be represented by x, and the larger quantity will be built using x. Okay, so once again, number of years sleeping will exceed the number of years watching TV. So this is the smaller quantity. Number of years watching TV. So in step 2, let's answer this question right here. The smaller quantity is years watching TV. And we're going to represent that by just x. Okay, and we write a little bit nicer. You can understand what I'm writing. Okay, so represent words with algebraic expressions. The words describe the number of years spent sleeping and the number of years watching TV. Okay, so years watching TV, just talked about it in step 1, is represented by X. And if you come back up here to the wording in the problem, it says the number of years sleeping will exceed the number of years watching TV by 19. So the number of years sleeping is going to exceed the number of years that you spent watching TV by 19. In other words, it is 19 bigger. Using the word exceeds is just another way of saying that. Okay, now let's continue to the next step in the 5-step process. Okay, so I guess I actually left the space for representing each thing, so I'll just do it again. Number of years watching TV, we decided was X. It was the smaller quantity, and we knew that because it said number of years spent sleeping exceeds, in other words, is bigger, and when you use addition, that makes it bigger, and it is this many years bigger. So you spent this many years over a 78-year lifespan watching TV, and this many years of that lifespan sleeping. Okay, the reason it's so important to label everything, which is why you are practicing this 5-step process, is so that you can go back and answer the final question properly without mixing up the two answers. So in step 3, it says write an equation that models the verbal conditions. The problem did state that the years spent on each activity are combined and the result is 37. In the wording of the problem, it says you spend 37 years sleeping and watching TV. So it's the number of years spent watching TV combined with the number of years spent sleeping is 37. And that is an equation that represents that particular sentence in the description of the problem. Example 4, solve the equation you created in step 3. The equation will yield one solution, which can then be used to find the other answer. This is where labeling the expression comes in super handy. Okay, so I'm going to solve this now. I have 1x and 1x is 2x plus 19 is equal to 37. I can bring this 19 to the right side of the equation, at which point it will be negative 19. And that'll bring me to this step right here. 2x, not x, I haven't gotten rid of the 2 yet, kind of jumping the gun there. So 2x is equal to 37, take away 19 is going to be 18, and then you would just divide by 2 on both sides, and that would give you x is equal to 9. And we're talking years here. So now you can go back to the labelings that you created up here at the top of the page. And this stood for sleeping, x plus 19, and this x stood for number of years watching TV. Okay, so it says here, this will be 9 years, and this stood for number of years watching TV out of that 78-year span. And then we have this expression x plus 19, which is the 9 that we got for x plus an additional 19, and that is 28 years spent sleeping. Okay, check the solution. It says that you spend a total of 37 years sleeping and watching TV. Do those answers give you that when you combine them? They do. So 9 plus 28 That would give you 37 total. So that checks. Okay, so breaking that problem down for you into the 5 steps that were discussed in the initial strategy for dealing with application problems. Moving to the next example. Use the 5-step process to solve the following problem. Median yearly salary of an American whose final degree is a master's degree is $70,000 less than twice what an American who has a bachelor's degree makes. So we have bachelor's degree and we have a master's degree, and they've given us a way to actually represent each one algebraically. So for the master's degree, it's 70,000 less than twice that of a bachelor's degree. So we're going to be using that key sentence as we go to create our algebraic expressions that we're going to eventually use in our equation. So what is the smaller quantity, the salary for the bachelor's or the salary for the master's degree? So the bachelor's degree is the smaller one. The smaller quantity should be represented as X, and the larger quantity will be built using X, in conjunction with the words that are described here. Okay, so represent words with algebraic expressions. The salary for the bachelor's degree, since it is the smaller one, we represent it with just X, and then we go back up to read the wording once again so that we can come up with an expression that represents the salary for the master's degree. Okay, reading this one more time. Master's degree salary is $70,000 less than twice that of the salary for the bachelor's degree. Well, here is twice the bachelor's degree, and then you're making $70,000 less than double this salary. So first you double the bachelor degree salary and then take away 70,000, and that represents your master's degree salary. Step 3, write an equation that models the verbal conditions of the problem. So as you went on to this next sentence after they were describing the relationship between the salaries, it said combined. Right there it tells you to add these two salaries. Combined, two people with each of these educational attainments earn $173,000. So right there we have a statement that tells us how to set up the equation in step 3. So we have the bachelor's degree salary plus the master's degree salary, and combined that is $173,000. Step 4. The equation will yield one solution, which can then be used to find the other answer. This is where, again, labeling your expressions comes in handy. Okay, so let's solve this. If we were to solve this equation that we set up in step 3, we would have 1x and 2x is 3x. We can bring this negative 70,000 to the other side, and that will be 173, 243, 173, but I'll just show it here. 173,000 plus 70,000, and you have 243,000. So once again, I moved the negative 70,000 to this side, at which point it took on the opposite side as it jumped from the left side to the right side. That's the same thing as adding 70,000 to both sides. When I combined 173 with 70, it was 243,000, and then I have to divide both sides by 3, and that'll bring me into a solution for at least x. Okay, so that is 81,000, and again, because you've labeled each salary with an expression, you can now go back and answer both questions. So the combined salaries, if you want to know what the two salaries are, I can put those right here. The person that has the bachelor's degree, so the bachelor's salary is just what we found for X, 81,000. We represented it as just X, and this is what we got for X. Whereas the master's salary was represented by this expression, 2 times 81,000 minus 70,000. So the person that has a salary based on a master's degree, this would be 162, and you can put in your calculator and then subtract 70. It will be the larger salary. So just 2 times 81,000 minus 70,000, and you get 92,000. So the bachelor's degree person makes 92,000 as opposed to the bachelor's degree person who makes 81,000 per year. Now it's stated in the problem that combined, the wording of the problem said combined, their earnings, the earnings of the two salaries should be 173,000. Does that check out? Okay, well, let's combine them. We are checking our answers based on the wording of the problem. Let's just make sure that that actually does come out to be 173,000 like it's supposed to. Okay, so we have 81 plus 92. And yes, it does check out. Okay, so we have done both problems illustrating the 5-step solving strategy discussed on the first page. Okay, now we get to some problems where you're not necessarily, in some of the problems, you're not necessarily representing two different things. So we'll read each of these problems to see how to set it up. And I will still be using the 5-step process as I go through this. I'm going to read for understanding. I'm going to come up with algebraic expressions to represent the unknowns. I'm going to try and represent one quantity in terms of the smaller quantity. I'm going to create an equation, and then I'm going to solve it and check it. So still using the 5-step process. I'm just not writing steps 1, 2, 3, 4, and 5. Okay, so Carla is asked about her age. Excuse me. She answers as follows. My age is 9 more than twice the age of my son. Now, since there are two people here, both having different ages, those would be the two things we could represent algebraically. We could represent the age of Carla, and we could also represent the age of her son. So these are the two things we want to represent. And I think I'm going to represent them right here. So let's do Carla's age and her son's age. Now remember, there is always one quantity that's smaller in these problems. Typically there is one that's smaller, and you're going to represent that one as X, and then you're going to build the larger quantity based on X. So the son is younger, that's the smaller quantity in terms of age. And then let's read again to see how Carla's age is represented according to the words in the example. Okay, so he's asked about her age, and she answers, my age is 9 more than twice the age of my son. Well, this would be twice the age of her son, and then 9 more than that would just be 9 added on to 2 times X. Okay, so then it says, how old is her son if Carla, this is Carla's age, if Carla Carla's age is 43 years old. So we take just her age because that's all they're talking about right here. Talking just about Carla's age. They don't say combined. They don't make any kind of a statement like that. They simply refer to just her age, saying that that age is represented by an equal sign in word problems. Is 43, and we solve. We bring the 9 over here. We subtract 9, which would be 34. 34. So we're going to go 2x on the left side, and you can do this in your calculator if you want to. 43 minus 9, 34. And then divide each side by 2, and you get x is equal to 17. We now know what x is, and therefore we know both ages. Okay, so now again, as stated in the previous two examples, you must label for each unknown. Okay, so this means that her son's age is 17 years. He's 17 years old. And she is, how old is, if she's 40? We already know she's 43 years old because it's stated in the problem. You could plug this in here. 2 times 34 plus 9, you would still get that she is 43 years old when her son is 17. And they only asked about the son because they had already told you what her age was about. Okay, so that's another one. Again, using the 5 steps, but just not numbering each step. Okay, in this next example, this talks about a reduction problem. Now, this one you don't necessarily have to label 2 different categories. So let's read the problem to see how we can come up with just something that represents a reduced price. After a 65% reduction, you purchase a new television for $171. Okay, so you could represent it in various stages. You could say, all right, you could go like this. You could say the original price of the TV is X dollars. And then there's a reduced price. Well, you have to know what the reduction is. It's being reduced by 65%. So what is 65%? It is represented like this. 65% of the original price. Of meaning multiply. That's how you represent multiplication. So you are going to reduce the original price of this TV by this much. This represents a 65% reduction when you take the original price and multiply it by 65%. You must use percents as decimals in your word problems. Whether they be banking problems, no matter what, you need to change the percents to decimal forms. So the new reduced price, doing this in stages, would be represented like this. It would be whatever it was at the beginning, whatever it costed originally, and then take off the reduction. So bring the price down using the reduction. Okay, it was this originally. It's being reduced. Reduce implies subtraction, that you're taking a certain amount off of the original price, and this is the amount you're taking off the original price, and that represents the new price. Well, they give you some information about that. They say after the 65% reduction, this represents after the 65% reduction. You purchase the new television, you get it for $171. So this represents after the 65% reduction. Okay, so they say after the 65% reduction, The price is, and again, this represents after the 65% reduction, that price is now $171. So now what you're going to do is just solve that. So you have 1x minus 0.65x. These are like terms, and you're just going to combine the coefficients. 1 minus 0.65. Okay, which would be 0.35. Put that in your calculator if you'd like. You're just putting the coefficients in there. 1 minus 0.65 is 0.35. Is equal to 171, and then you're going to have to divide each side by 0.35. So come up here, continue by dividing this side by 0.35 as well as this side. And you're trying to find the original price, which is what X stands for. And we are about to solve for X. So rounding off to dollars and cents, as you are asked to do right here, 171 divided by 0.35. So this TV originally cost $488.57. Go 2 places to the hundredths place after the decimal to get to dollars and cents. $488.57. Okay, so that's that one. Okay, this problem is similar where you're having either, an increase or a decrease. That's what these two problems are examples of. So in this one it says, including a 2% sales tax, a hotel charges $183.81 per night. Find the hotel's nightly rate before taxes included. Okay, so nightly rate before taxes. Okay, let's see. We don't know what that nightly rate is. In fact, it's the question. Okay, then as we read this, we understand that we know what the total bill is. It's $183, but that total bill included the nightly rate, the base rate of a room, plus it included a 2% sales tax. How do they do a 2% sales tax? They do 2% of the original rate. So this represents 2% of the original rate. So just like the last problem, you have a basic cost of an item, just like we had a basic flat cost, it represented the original price. Well, we have the base rate of the room before taxes. In this problem, we had a reduction, and in this one, we're having an increase. So the increase in rate due to taxes, that increase is going to be like this. It is 0.02, in other words, 2% of, meaning multiply, of the base cost. So pretty much just like the last one, only here you were talking about reducing the price. You're getting something on sale, and you were told what the sale price was. It was $171, and that enabled you to find the original price. Here, we're just talking about the fact that the price is going to go up, not down, because they're adding something onto the base price of the room, and the base price plus the tax added in is $183.81. Okay, so like the previous problem where we combined like terms, here we combined them through subtraction, here we're combining them through addition. So it is 1 plus 0.02 for your like terms, and that gives you 1.02 is equal to $183.81, We are still trying to find the base price of the room before that tax was added on, because the 183 includes base price plus tax. So divide this 1.02 off of the x, likewise over here, and you get that the base price of the room was 183.81. 183.81 divided by 1.02, just putting that in right there. So the base price of the room was $180.21. Okay, so that's another one of those. Okay, and I also threw in here a very typical kind of problem that you're going to see in an algebra class at this level. This concerns interest, an investment that you're making in an interest type situation. So let's read the description of this example. It says Jesse puts X dollars into an investment with an interest rate of 5% per year, and Y dollars into an investment with an interest rate of 10% per year. She invests a total of $4,200, and her interest earnings after 1 year are $310. So this can be somewhat of a complicated problem for students, but if you try to get organized like I have, create labelings, represent each of your labelings, you can wrap your head around this type of problem. So let's read this again. A lot of times you got to read it 2 or 3 times. She puts a certain number of dollars in an investment with an interest rate of 5%. So she's got, let's see, I'm going to put it down here. She's got a 5% account, a 5% interest account. Remember, we always represent percentages using decimals. So got one that bears interest of 5%, and then there's also some money being put into a 10% account. Okay, we got one with a rate of 5%, another account with a rate of 10%. 10% interest, this will be how we'll represent it when we write our equation. And it says we put X dollars into the account bearing 5% interest. X dollars are put there. And we put Y dollars into an investment with an interest rate of 10%. So there's Y dollars in this account. So we try to create equations based on the rest of the words in the problem. Each sentence is going to give you a certain amount of information. So it says she invests a total of $4,200. Well, these are the dollars that she walked into the bank with. She had $4,200 and she put some of it in here and she put some of it in here. So state the system of equations to be solved. The money that she put in the 5% account plus the money she put into the 10% account totals $4,200. At this time, you do not know how much she put into each account. So that's one equation that you could work with. We are creating a system of equations, meaning that there's more than one equation, and we're going to solve them simultaneously through the methods of solving a system. Okay, so let me get this out of here so in case I need this space to solve. Okay, another equation that you could come up with, and I think I'm going to move this over a little bit. Just move this over a little bit. You can understand that this is equation 1. I came up with this simply by knowing that this is the number of dollars that she walked into the bank with. She dumped some of it at this counter for the 5% account, and then some of it at another counter where she's making an investment at 10%. This is the rest of her money. But altogether, those monies add up to $4,200. So I have one equation. But I can also make an equation that talks about the amount of interest that she is going to earn over the course of the year. When you're earning interest, it is principal. That's the amount that you invest in the account. In this case, it would be X dollars times the rate times time. Well, in this case, we are just looking at how much is being earned over the course of 1 year. So time is typically in years, and it will just be 1 year, so we're just going to have a 1 in there. So really, we can just go principal times rate, because multiplying by 1 is not going to change anything. So this is the principal right here, the P that you see in the formula, because this is the typical formula for calculating interest. So the principal is X dollars. You want to multiply it by the rate. That's this R right here, which is 0.05. 0.05 times X. Then there's also interest being earned off of this account. Same formula, principal times rate times time, but again, time is just over the course of 1 year, so we'd be putting a 1 in there. So just principal times rate will do it. Here, this is the principal. That P for, so this is the amount that's invested at 10%. So for this account, you are earning interest, which is calculated by 0.10, that's the rate, multiplied by the principal. Rate multiplied by principal. Now let's see if it talks about how much interest. It says, and her interest earnings after 1 year total $310. You don't have to put the dollar signs, you can just put the dollar amount, so 300. So in this way, we have created a system of equations. Now let's see, I didn't answer these questions here. State the equation that describes the total investment. That was this first one that I came up with. I guess I made separate spaces for these. State the equation that describes the interest, and I just discussed that with you. This represents the interest off of the 5% account, and this interest represents the interest off the 10% account. And they make the comment here that the interest after 1 year is $310, which is what gave me the thought to add these two amounts of interest that are earned over the course of a year, totaling $310. Okay, from this information we can create two equations. I've done that right there. And we can begin to work these out. So if you are trying to work this system out, you're going to want to, pick a method. You can either use substitution, or you can just try and line up the X's, line up the Y's, and try to get either the X's or the Y's to go away through elimination. Either one is fine. So let's say that you were going to try and get the X's here to go away. And you can get rid of these decimals, or you can work this system with the decimals in it. It doesn't matter. But if you are going to use the method of elimination, let's say you wanted the X's to go away. When you're doing elimination, you add the two equations together. So if one of the equations has the same coefficient right here that this one does, in other words, a 0.05, but with a different sign, and I'm going to give myself just a little bit of room to get some work done here. So I'm going to back this up a little bit. So if this had a 0.05 here but negative, when you add them, the X's would cancel out if you have forgotten the process of elimination. So I think that's what I'm going to do. Move this over just a little bit. Okay, so right now I have an X. It has a 1 in front of it. If you want to change the coefficients so it has a negative 0.05 in front of it, you make changes by just multiplying the equation by the constant that you need to multiply it by to create the proper coefficient. So right now this is a 1. I am going to multiply this entire equation by negative 0.05. Okay, so that'll turn into this. Negative 0.05x. You're going to use your calculator to help you. Negative 0.05 times y. That's easy enough to do without a calculator. And then negative 0.05 times 4,200. Might want to use your calculator for that. Negative 0.05. Clear this out. Times 4,200 gives you negative 210. Okay. So, this doesn't look very good. Let me just write a little bit nicer. Okay, it's a little bit clearer. Okay, so what we're doing is we're combining this equation with this equation. We're just combining those, making sure to combine like terms. So when we combine these x's with these x's, again, we are adding these two equations together to get a system solved. Just reviewing the steps for solving an equation. Okay, so negative 0.05x combined with positive 0.05x would get the x's to go away. That is the whole point behind the elimination method. You play around with the coefficients, trying to get the same coefficient on one variable as you have in the equation below it, only with opposite signs. Because if they don't have opposite signs, then they're not going to cancel when you add them. Okay, so we got negative 0.05 happening here just by multiplying everything. Because if you multiply one term by negative 0.05, you have to multiply all of them, or else you're not dealing with the same equation that you just had a minute ago. It has to be equivalent. So it gave me negative 0.05x, negative 0.05y, and a negative 210 when I multiplied 4,200 times negative 0.05. I left the bottom equation as is. I am now adding them up column by column. So x's added with x's cancel. Negative 0.05 combined with positive 0.10. Again, I'm sure that there are many of you that can do that in your head, but if you can't, just put it in your calculator. Negative 0.05 plus 0.10. So just 0.05 for your y's. So this is what I have left. X's are gone, but I do have y terms left. When I combine this, try and write a little bit better. When I combine this negative 0.05 with this 0.10, I get 0.05 for my y terms, and now I'm going to add my column of constants. So negative 210 combined with positive 310. You can put that in your calculator, negative 310 plus 310, and you'll get 100. Okay, so now I'm down to just one variable in my equation, and all I have to do is divide off that coefficient of 0.05 here as well as here. And I end up with y is equal to, and then 100 divided by 0.05. And that gives me 2,000. Okay, because I have labeled everything properly and clearly, I now know how much is in each account, because I can go down to these labelings that I created at the very beginning of the problem. That is a big issue for students, getting these model application problems wrong, because they don't label anything and then they accidentally swap the answers and end up getting it wrong. They have the answers backwards. So please start off the problem. That's what every one of these examples has illustrated. How to label things so that you can answer the question properly at the end. So Y is 2,000. Y stands for the amount that was given at the 10% interest desk. So 2,000 was given here. And then I believe they said that in this problem, a total of 4,200. They walked into the bank with 4,200. So if 2,000 was given here, then this would have to be the rest of the 4,200, so 2,200. If you can't do that in your head, it would be what you walked into the bank with minus how much you know you gave at the other counter. So you're given part of your 4,200 at one counter and the other part for some other investment. So that's 2,200. Okay, and then you have both answers. Okay, so I have done what was required here. 5% amount was 2,200. And 2,000 was for the 10% account. Okay, so now we get to linear equations that exhibit consistent trends in growth or decline. I'm going to exhibit growth first to give you an example of growth first, and then I'll give you an example of a decline problem. So this example says in 2014, the average age of cars on U.S. roads was 11.3 years of age. For the period shown, this average age increased by approximately 0.2 years per year. If this trend continues, how many years after 2014 will the average age of vehicles on U.S. roads be? When will it be 12.3 years? In which year will this occur? Okay, so let's see. What is the average age of cars when the observation began? So we'll just look here. It says year 2014. Average age of cars on the U.S. roads, this is when they began the observation, is 11.3 years, 11.3 years old. That's the average age of a car. Okay. What number represents the consistent growth trend that occurs each year during the observation period? Well, that would be the number that they're talking about that's happening each and every year. So that would be this amount. The age of the car, average age of a car is increasing approximately 0.2 years each year. Okay, so that would be the 0.2 years each year. Plot the average age at the beginning of the observation, meaning that at 0 years there's a particular average age. Label the x-axis with the word years, assigning 0, 1, 2, etc. to the x-axis. So they're kind of giving you the scale that you're going to use on the x-axis. Okay, so this will be years going along our x-axis. And this will be 0, 1, 2, etc. 1, 2, 3, 4. I'm not going to label every single one. Let's just go every other one. So 5, I'm going to do 6 right there. That will be 7. This will be 8. This will be 9, 10. And then 11, and then 12 will be all the way down here. And then along the y-axis, Let's see what they say. Label the x-axis years. Label the y-axis age of the car. Okay, so that'll be our labeling there. All right. Right, so then it says, and for here, we're going to jump in increments of 0.2. So this will be 0.2, 0.4, 0.6, 0.2, 0.4, 0.6, and then it'll be 0.8, 0.10, etc. Okay, so now let's see. What is the y-coordinate for the point that has x, an x-coordinate of 0? Well, when you're at 0, that suggests the very beginning of this observation when you were at 11.3 years old. Okay, so let's see. This would be 11.3. I might have to put these down here. I didn't leave that much space. I'll write it out here. At 0, when we began observing these cars, we were at 11.3. So maybe this might not work. We might have to, I'm going to change that. Let me slide this up. We're going to jump in increments of 0.2, but as far as being able to graph things, we're going to have to change the scale here on the y-axis. So first let's fill in these points and see what kind of points we have to graph. So then at 1, it's going to jump in increments of 0.2 every year. So when you're at 1, it's going to be 11.3 plus 0.2. I'm sure you can do that in your head, but if not, here's 11.3 plus 0.2. We're jumping that much each year. And then at 2 years, we're jumping 0.2 again. So I added 0.2 to get to this. I'm going to add 0.2 to get to this, and this would get you to 11.7. Okay, so in this particular problem, when we first start, let's see, let's call this, see how I'm going to do this, make a decision about this. Label the x-axis 0, 1, 2, 3, 4, 5. Okay, and then here, I'll just call this 11.3. And then I'm going to go up and call this 11.5. I'm going to call this 11.7 and so forth. And you can go as far as you need to, but I'm going to plot some points right now. So this is where we are originally when we begin our observation of this linear growth trend. Then at 1 year, we're at 11.5. And then at 2 years, we're at 11.7. And so what I wanted you to see here was that whenever there is a consistent jump, either up, representing growth, or down, representing decline, you are going to have points that line up in a linear fashion. And that is what's happening here. This was the original observation at 0 years, meaning the observation had just begun. Then a year out, we were 0.2 up. Then a year out, we were another 0.2 up. And you can continue, but they would all line up in a linear fashion simply because of the consistency in the growth rate. This growth rate is known as the slope of the line. So you could actually write the equation of this line. What formula allows you to write the equation that models this line? Well, the slope-intercept formula. Okay, this slope right here that we were talking about is that consistent rate of increase of 0.2. And the y-intercept, well, the y-intercept is the point where x is 0 and you have a particular y coordinate. This actually stands for the y coordinate. So that was 11.3, the actual original average age of the car. Okay, this is m in this particular equation that I'm about to write, and this is the b value. The original average age at 0. That's what a y-intercept is. So writing this more specifically, it would be y is equal to your slope or your consistent growth increase is that 0.2. So we'll put that in as m. It'll be the coefficient of x plus the 11.3. This is the equation that represents the line that you're seeing here visually. Okay, use the linear equation to solve the following problem. When 12.3 years is plugged in for the appropriate variable, you can then solve for the x value associated with 12.3 years. Okay, so the x values, these values that you see here are years. Okay, these are your x variables, the quantities that represent x. So when it says years, and that's the use the linear equation, when 12.3 years is plugged in for the appropriate variable, then you can solve for the x value associated with 12 years to find the final question. Okay, so that we have the age of the car, which is also in years, and this is how many years it takes for that average age of the car. So we're going to go, let me go grab that equation again, 0.2x plus 11.3. So we're going to go here. $12.3, that'll represent the age of the car, and then we can solve for the x value associated with a 12.3 old car. That's how many years old it is. This will be 0.2x plus 11.3, and we're going to solve for x. Okay, so we can bring this over here. You'll have a 1, you'll have a 0.2x here, and then we can divide by 0.2x, 0.2 on the left as well as the right. And we end up with 1 divided by 0.02. So jumping in increments of 0.02, that would take 50 years. Okay. Let's move on to a decline problem. Give me 1 minute and I will continue with the next problem. Okay, so this problem has to do with decline. This problem is similar to the last problem, except that there is a consistent decline rather than consistent growth. What does that tell you about the sign of the slope? So when you're declining, in the last problem we had a consistent growth, and that was 0.2 each year. The average age of cars that are out on the road was going up by 0.2, so the slope was positive. But in this problem, we have a steady decline, and that is depreciation on a car. So the problem is similar to the last one, it just has a negative slope rather than a positive slope. Write the formula that models the car's value, Y, in dollars after X years. So we're going to use the equation of a line formula again. Okay, we're going to say that the starting value, that represents the y-intercept. And then it's depreciating by $3,000 a year. So let me move this over. Steadily going down by 3,000, that's why there's a negative there, per year. So the only difference in this problem is that we're going down by a steady amount each year rather than up. What is the car's value at 0 years? Well, X is the number of years that have transpired, and Y is the price of the car at that particular time stage. So we could go Y is equal to negative 3,000. Question is, what is the value at 0 years? Remember, X is the number of years. So if anybody gives you a number that has to do with the number of years, it goes in there for X. You have to be clear about what the variables stand for. So you put a 0 in there, and just like you would have imagined, they did tell you what the original price of the car was, so it makes sense that at 0 years it turns out to be 24,000, because this times this is 0, 0 plus 24,000 is 24,000, so that makes sense. Use the formula from part A to determine after how many years the car's value will be 9,000. Okay, so we just have to make sure to get this 9,000 in the proper place. It doesn't stand for years, it stands for a certain price that the car is now at. Okay, so using this formula, you put 9,000 here. Hold on, I'm gonna have to get some water. Okay. Okay, so if you continue to solve this, you're just going to bring the 24,000 over to the other side where the 9,000 is. And you end up with 9,000 minus 24,000. And that turns out to be negative 15,000. And negative 3,000 over here. Then divide each side by negative 3,000. And you get 5. Okay, I think I'm going to stop this video. I've obviously talked too long. I'm kind of losing my voice here, and I will pick up in the next video.